Last time we discussed motion of a charged particle in a uniform magnetic field, and we took very general approach and found that if you send a particle with some initial velocity v naught, which you call x direction. So, you send the particle with v naught in x direction, and then you have a magnetic field in z direction. So, perpendicular to the magnetic field we are injecting it, and then we wrote force is equal to q v cross b, and from there we wrote the x component of the force, y component of the force, z component of the force was 0 because it is q v cross b. So, if b itself is in z direction, v cross b has to be perpendicular to z direction. So, that force was not there and there was no initial velocity assumed, and therefore, the whole motion was in xy plane. Then we derived the equations, the position and the x position and y position at time t, when t equal to 0 is taken here, is derived as x equal to v naught by omega sin omega t, y is equal to v naught by omega cos omega t minus 1. What is this omega? What is this omega here? This omega is qb by m, that is omega. The charged particle, the charge is q, its mass is m, b is the magnitude of the magnetic field. So, this quantity is named as omega, and it is a very appropriate symbol, appropriate name, because you see, if I call this as omega, then your x and y are coming as something like sin omega t and cos omega t. And velocities are also derived. Velocity is v naught cos omega t, vx is equal to v naught cos omega t, and vy is minus of v naught sin omega t. So, we have complete description of the particle, what it will do. At time t, I know its x coordinate, x position, I know its y coordinate, y position, I know the x component of the velocity, y component of the velocity. So, entire motion is here in these equations. But now, from these equations, I have to connect to the actual motion which is taking place in that world, in that region. So, that is our task now, next task, that using these equations, what is the path of the particle, and all those things we will try to derive from here. Alright, so let us make some space. We will be keeping this x and y essentially, we will be needing this, rest of the things I can erase. We would like to get the equation of the path. We do have equations of the path here, x as a function of t and y is a function of t. So, it is a parametric equation of the curve, but we can get a direct equation if we eliminate t from here and get a relation between this y and this x. So, what we do is x is equal to v naught by omega sin omega t, let us write that, x is equal to v naught by omega and sin omega t. Remember what is omega? Omega is, as it is written here, qb by m, and y, if you write what is v naught by omega cos omega t, v naught by omega cos omega t, what is this? This will be y plus v naught by omega. Verify that I am writing it correctly. This side I am writing v naught by omega cos omega t. So, v naught by omega cos omega t minus v naught by omega, which I will be shifting to the LHS, and then it will become y plus. So, this side is y plus and v naught by omega. This y, and then this minus v naught by omega comes this side and becomes plus v naught by omega. So, that is plus v naught by omega here. Now, to eliminate t, just square and add. So you get x square plus y plus v naught by omega square is equal to v naught by omega square and into 1 sin square omega t plus cos square omega t, that is 1. So this is the equation of the path. And what is this equation? What curve is this? This is equation of a circle, right? If you write x minus alpha square plus y minus beta square is equal to some r square, this is equation of a circle with center at alpha beta and radius r. If alpha beta are 0, if the center is at the origin, then it is x square plus y square equal to r square, and that is the standard first equation that you learn about the circle. Now here if you see this alpha is 0 here, so for this if I write center will be at 0, x coordinate will be 0 and y coordinate will be minus v naught by omega. So minus v naught by omega. So this is the center. Y minus beta, alpha beta is the center, y minus beta, here it is y plus v naught by omega. So the y coordinate of the center will be minus v naught by omega. And radius, so radius is v naught by omega. This is the radius. First let us look at the dimensions. First let us look at the dimensions. If we have not made any mistake, then the dimension should be consistent. Let us see that. V naught by omega, this is x coordinate, this is y coordinate. So this should be length, and here also radius is v naught by omega, so this should be length. So let us see what is this v naught by omega. So v naught by q b here and then m here, and this you have to check that this is essentially length. You can see it from here. You can see it from here. This omega is 1 by t, 1 by time. How do I say that? Sine of omega t, cos of omega t. So if you are getting sine of omega t, this omega t should be a number. You can take sine and cosine only of a number. You cannot take sine and cosine of a length or time or force. It has to be dimensionless. So omega has a dimension of 1 by t, and if you use that, this is 1 by t. So this t goes here, velocity into time, and that is length. Perfect. Perfect. So now come to the original situation, physical situation that we started with. What we had was, we started our journey where you have magnetic field in the z direction. So this is x axis, this is y axis, z axis is coming out of the board, right handed system. I cap cross j cap should be equal to k cap. So z is coming out, and everywhere we have a magnetic field in z direction having the same magnitude b. Everywhere. It's not easy to get a uniform magnetic field in a big area. Is not very simple. Experimentally you have to make a lot of effort to get uniform magnetic field in a extended region, but nevertheless for our interest we assume that. And we started with that here is a particle at t equal to 0, this charged particle is given a velocity v naught, this is at t equal to 0, and then we leave it and then the magnetic field will decide the fate. Okay. So, this particle has to go on a circle. Which circle? This circle, Where is the center? 0 comma minus V naught by omega, and V naught by omega is this, mass times V naught divided by QB. If your speeds are non-relativistic, you can write this as linear momentum and Q times B. So, that is V naught by omega and minus V naught by omega. That means it has to come here, somewhere here. This is the center, minus V naught by omega. You calculate what is V naught by omega. V naught is given to you, magnetic field is given to you, charge on the particle is given to you, mass of the particle is given to you. So, you know what is V naught by omega. That much distance in the negative y direction, here is the center, and the particle is here and going in this direction, and this has to be center. So, what kind of circle it will be? It will be a circle of this kind. Below the x-axis of this radius, center here. If the particle has a negative charge, if this q is negative, then everything will be reversed. If this q is negative, and then this V naught by omega will be negative, and minus of V naught by omega will be positive, the center will be here. So, if you have projected the particle in this direction and you have a negative charge, then the center will be here and you will have a circle of this kind. Okay. So, it has to go on a circle. If positive charge, it bends downward, negative charge, it bends upward. Similarly, if you reverse the direction of the magnetic field, then also you will get this way or that way. And since the initial velocity is here, then this will be clockwise and this will be anti-clockwise. So, it can be clockwise, it can be anti-clockwise, and so on. So, that is the path of the particle. Okay. Next is, we have assumed that our velocity is in x direction, or in this plane, xy plane. If it is in xy plane, then also the same story. What happens? Suppose it is in xy plane, the initial velocity is this way. Suppose this is the initial velocity and you have a magnetic field. You have a magnetic field, uniform magnetic field. What will happen? Simple story. Why should I take this x-axis? No, it's our choice. We can take the x-axis this way and we can take the x-axis, y-axis perpendicular to it. Same situation. If it is positive charge, if the magnetic field is coming out of the board, then this center will be here. On the y-axis, negative y-axis, and therefore it has to bend this way. Otherwise, if it is negative charge or the field is in opposite direction, it will bend that way. So, this is very simple. You calculate what is the direction of the force. Another thing is, forget everything. Remember this, that radius has to be m times v naught divided by qb. So, you know the radius, and if you know the radius, you can very easily locate the center. So, need not use axis at all. If you suppose you have a, let me take that reverse so that you also get experience of that. Suppose the magnetic field is going into the board. Uniform, and then the particle is given some velocity in this plane perpendicular to the magnetic field. What is, and it is positive charge, and this is the velocity given. So, what is q v cross b, direction of this? direction of this v cross b. This is velocity, and then the magnetic field is going inside the board. So what will be the direction of v cross b? If the magnetic field is coming out and this is v and this is b, you turn it this way and therefore you will go down. Opposite, the force will be in this direction. This force will be in this direction. So it should bend this way, not this way. And hence on this perpendicular line, you locate the center, in this side. See the direction of the force, and that decides whether it is on this side or whether it is on this side. And the radius is this m times v naught by q into b. So that much distance you locate the center. Once you know the center, once you know that this is the radius, then you can immediately write the path. So that is it. And if there is a z component also, so this is most general situation for initial velocity being in this xy plane, that is perpendicular to the magnetic field. But then if you also have z component of initial velocity, then what happens? Nothing great. In x and y direction your equations are identical. In x and y direction your equations are identical. In z direction fz is 0, because your b is taken in z direction, or z direction is taken along the given magnetic field, and hence v cross b, which has to be perpendicular to b, also perpendicular to v, but it has to be perpendicular to b, and therefore this q v cross b will not have any component in this direction. It is perpendicular to this direction, and therefore fz must be 0. Acceleration must be 0. If you have given some initial velocity in z direction, it will remain the same. So it will go in z direction, z direction, z component or z coordinate of the particle will continuously and uniformly increase at this rate. Whatever initial component of velocity is there in z direction, with that it will continuously increase. But in x and y direction, if you only see, then yes, it is still going in a circle. So it is going in a circle in xy plane, and at the same time it is going up, it is going in z direction with a constant initial velocity. Whatever initial velocity is given, with that it is going, and therefore it will make a spring, like this, spring like motion. It is called helix. And in one rotation in xy plane, how much is the displacement in z direction? That is called pitch. This length is called pitch. So in one complete revolution in the xy plane, for that you know how much time it will take. This omega is here. And this happens to be the angular velocity, because here are the equations, sin omega t, cos omega t. So it happens to be the angular velocity, and therefore the time will be time period will be 2 pi divided by omega. So 2 pi divided by q here, b here, m here, and that is the time period. So it completes one circle in the xy plane, x coordinate and y coordinate only. If you only see that, it is still a circle, and one full revolution means this much of time. And how much is the displacement in z direction? How much will be this pitch? It is the distance covered in z direction in this much of time. So this will be equal to 2 pi m by qb and into v naught z. So this is the time, and this is that velocity, and you multiply, you get length, and that is this pitch. Now, this kind of deflection, if the particle is going in some path and you put a magnetic field, it enters the magnetic field perpendicularly, charged particle moving, and then at a certain region it encounters a magnetic field. Let me show this situation. So, suppose a particle, charged particle Q is going with some speed v naught, and then all of a sudden it encounters a region where there is a magnetic field. So, there is a region in which you have a magnetic field. Let us say this is the region where you have a magnetic field coming out of the board or going into the board, does not matter. And it is not uniformly spread in a very large region, so it is a small region. So, when it enters here, and the speed is large, of course, quite large speed, so it will bend. In this situation, taking it as a positive charge, this is velocity, and here is the magnetic field, and therefore V cross B will be downward. So, the center will be somewhere here. Center will be somewhere here. And how much is the radius? The radius is that V naught divided by omega, which is Q into B into M. Now, if this V is large, initial velocity is large, the center is quite large. This radius is quite large, and therefore the center is far, far away. There may not be any magnetic field here, but still the center will be here. The magnetic field is only in this much region, but the center does not need a magnetic field, and with this big radius it will turn. So, the circle will be something of this sort, big circle. Will it go in a circle? Will it complete the circle? It will not, because once it reaches here, there is no more magnetic field, no more bending, and therefore it will go on a straight line, draw a tangent to this, in this line it will go. Will the speed change? We erase that Vx and Vy. But in Vx and Vy, one is sin omega t, one is cos omega t, some constants are there. So, that Vx square plus Vy square, you will see it is just V naught square. It goes on a circle, but the speed does not change, right. Magnetic field can never change speed of the charged particle on which it exerts force. Magnetic field can only change the direction, because magnetic field is always perpendicular to the velocity V cross B, Q V cross B. So, it can only change the direction of motion, but cannot change the speed. So, with this same speed V naught, it will go in this straight line now. Now, this has a huge applications. By the way, I have given this rectangle, but that rectangle is not needed. This magnetic field is not used, this magnetic field is not used, this magnetic field is not used. Even if you have a circular region, so that this path is the same inside the magnetic field, is the same story. So, this has many applications. I will just try to tell you two of them briefly. One is where we have accelerators. We have particle accelerators, where charged particles means you take the particles, neutral gas for example, and then that gas is injected, and then there is some chamber, some mechanism where you strip one or two electrons, take out one or two electrons, and it becomes ion, positive ion, is charged now. And this particle is now sent with certain velocity, certain speed in a tube which contains electric field. That means, let us say we have this tube which we call accelerator tube. So, in this side you are giving a particle is going here with certain positive charge, you have taken 1 or 2 electrons, say helium plus for example, or helium plus plus for example, and then there is an electric field here. In this you have electric field. So, you apply appropriate potential differences, batteries or power supplies, and create an electric field. What will electric field do? It will change the speed. The magnetic field will not change the speed, but electric field can change the speed. So, if the direction of the electric field is same as the direction of the velocity, then it will change the speed, it will increase the speed, it will accelerate the particle, but it will go in the same direction. So, depending on how much field you have applied, what is the length, what is the potential difference at the end, this comes out here with a great velocity. So, here it enters with a very small velocity, but here it comes out with a great velocity. That is the role of particle accelerator. And why do the people use all this thing? They accelerate the particles because these highly energetic particles can do lot of material synthesis and other things. You can study many phenomena using these particles, and for that you need big apparatus or chambers and things like that. So, suppose I have some equipment here for doing some useful work, and then these particles are going here and doing your work, that is fine. But generally with one accelerator facility you have varieties of uses, 3-4 uses at least. If you have 3-4 uses, then every time dismantling it from here and putting up a new apparatus here, because these operators are also many times they are not small apparatus, they also are huge setups. So, that is very difficult and not practical. So, equipment 1 is here. What they do is they set up another equipment for the second kind of experiment. They will set up this equipment 2 here. Then for some third kind of experiment they put up equipment 3 here, and then here they will put a magnetic field. So, some kind of currents, and that currents will produce magnetic field, and when this enters here, if the magnetic field is switched off, then straight goes into this equipment, the beam goes into this equipment. But then if the magnetic field is applied, then it will bend. So, depending on what is the direction of magnetic field, it can bend downward, it can bend upward. So, if you are applying, and you can adjust the magnitude of the magnetic field because they are controlled by the currents, then you can make it bend and go straight into this equipment. Or if you reverse the magnetic field, apply appropriate magnetic field, you can bend it this way, and then it comes out, it goes straight into this. You can have 3, 4, 5 such equipments, and this magnetic field here can switch this beam which is coming to this equipment or that equipment or that equipment, and so on. I will describe one more use of this kind of deflection in laboratories where we do varieties of research next time.